Now we'll look at an example which is connected but not path connected, and anyway is a nice example in working out with definitions, topology. So this is what's called the topology sine curve. Before drawing it, let me first write a set A. A itself is not the topologist kind sine curve. It's the graph of a function. So it's going to be x and sine of pi over x, where x belongs to, the pair where x belongs to 0, 1. Okay, I could take 2 pi over, it's qualitatively the same, or anything like that. In fact, I could even take 1 over, but it's nicer to write when you say sine pi over x, because that means when x is 1, sine pi is 0. So you start here. And let's see what happens to this graph. The thing is that, okay, if I mark a few points on the axis, so here is pi. Pi over 2 is going to correspond to, when x is half, this becomes 2 pi, which is x is half. And then when x is 1/3, this becomes 3 pi. So 1/3 is somewhere here. And then you have 1/4. And at all of these, it passes through the origin. And in between, it oscillates. So as you see, this is a function that goes down here. It's not very true because it's getting sharper, goes up, goes down, goes up, and then keeps oscillating more and more rapidly. It's a graph. Oh, sorry, that was a bit drastic erasing. It goes down first, we have because of our choice. You could use 2 pi if you don't want that to happen, but it doesn't make a difference for what we are saying. So this is a graph of a function. It starts oscillating. I have marked the -1 and 1 line. It oscillates between that. And it oscillates more and more rapidly, eventually oscillating infinitely many times, because at each 1 over n it's hitting the origin. And between that it's going alternatively up and down. So let's stop drawing this. I think I learned the hard way. I should not undo or the whole stroke goes away. Okay, so here it goes. And let's just dot it on further. This oscillates infinitely many times, but what is called a topology sine curve. So you see it has everything here as a limit point, and so topology sine curve is A bar. So this is the set we are considering. This is the closure of A. It happens to be A union. It's fairly easy to see. All points in A, of course, are in its closure by definition. Any point here or here or here is not in the closure. But exactly every point between this and this is in the closure. So you can as well draw a line between these two in this lighter blue. This part is in A bar, but not in A. Okay. So that is the thing. So A bar is A, not equal to, union, union, the set of points of the form 0 and y, where y is in -1, 1. Okay, what do we know of these as topological spaces? So this is homeomorphic to, I can make it a separate thing and then introduce some notation here. So A is homeomorphic to 0, 1. And indeed, you can see the inclusion using, in one direction, S goes to x, x goes to x, sine x. Sine of pi over x. So a continuous map from A to, so this is the map from open 0, 1 to A. And the notation I wanted to introduce here is P project onto the x direction. So this maps xy to x. So on A, we'll take the same thing. So I'm going to say let py map xy to y. These projections will be very important to us. We'll take them on various sets. Okay. So A is homeomorphic, hence it's connected. Therefore, A bar is connected. Okay, so we need actually this picture. So let me so x map sine 1 by x. Okay, we'll take this picture on a fresh page. So let me write it out more fully. Hence A is connected. So indeed it's an easy exercise that the graph of a function is always homeomorphic to the domain. Hence A is connected, hence A bar is connected. So it actually looks like it has two pieces given by the two colors, and these are path components, but they are actually not components. We cannot decompose. That's because if I took any open set here, like this one, it's forced to hit a little bit of this blue region, and then it can't be disjoint, because if you intersect the blue one and you're an open set, you have to be all of it. That's really just in the special case the proof that the closure is these. Okay, so the claim here is the proposition A bar is not path connected. And specifically, let's identify a pair of points here. There's this point 0, 0 and 1, 0, and we'll claim that there is no path from A to A bar. That is the main thing we'll prove. Okay, it also nicely, as I said, illustrates lots of things that we have been working with in set topology. So to resume, I've copied this picture because we'll explore it in detail. We claim there is no path from 0, 0 to 1, 0. Let's assume there's a path and we'll find the contradiction. Okay, contradiction to continuity. So let alpha from 0, 1 to A bar be a path, and let alpha of 0 is 0, 0 and such that alpha of 1 is 1, 0, and we will contradict it being a path, which recall includes the fact that it's connected. So suppose we have such a path, we want to see this. So now what happens to this path? It starts at 0, and for a while it might remain in this light blue region oscillating, and then at some point it leaves, and then it ends up at 1. Okay, eventually it ends up at 1. Not here, it has to go along the curve. So the last part would be somewhere along the way, it ends up at 1. Okay, and it's where it makes it a leap that it has a problem. So let's capture the point where it makes a leap first. We'll use our projection maps, Px and Py. Okay, and so let T0 be the first point where it makes a leap, which could be 0 itself. There's nothing that says it should stay here for a while, but our definition will include that case. So we take the largest point, supremum of all those points, tau, let's say, in 0, 1, close 0, 1, such that Px, that is the x coordinate of alpha of t, is equal to 0 for all t in the I could write interval, but the interval is necessarily could be degenerate for all t such that 0 is less than or t is less than or equal to tau. So I look at the point tau, the largest point or the supremal point, so that up to that point Px of alpha of t is 0. Okay, so we'll let alpha equals alpha x, alpha y. It may be a little more convenient to use the notation. So alpha x is, of course, then alpha x is Px composed with alpha, and alpha y is Py composed with alpha. So remember, these are also continuous. So this could be just written as alpha x. So it's easier to think of it this way. So alpha x of t is 0. Look at all points, and then we claim that it's not going to be not continuous at this. Well, what is the idea? We'll take a ball around the image of this point. Okay, so first of all, we can claim we see alpha x of t0 equals 0 by continuity. Okay, why is that? As tau less than well, There are a couple of cases here. One case is where tau t0 is equal to 0, in which case we know it by definition, as let's say if t0 is greater than 0, okay, then t0 is a limit point by construction of alpha x inverse of 0, okay, because every point in this set is in alpha x inverse of 0, and a supremum of a set is a limit point of an infinite set. That is as sup is a limit point. Sup s is a limit point of S. If S is infinite. So T0 is an alpha x inverse 0 closure. But this is closed, equals alpha x inverse of 0 as as inverse image of a point. A point is closed in R as alpha x inverse of 0 is the inverse image of a closed set, so it's closed. So we know at t0 you're at this point. So maybe this is where you are at t0. So let this be alpha y of t0. Okay. And now we'll take a delta neighborhood. Okay, so let epsilon neighborhood. We'll take epsilon is, let me take half is good enough, even 1 is good enough. Okay, let's just take epsilon is 1, because the distance between -1 and 1 is 2. Okay, and find delta greater than 0 such that if t belongs to t0 minus delta, t0 plus delta, okay, well, intersection 0, 1 if t0 is 0, but those degenerate cases I won't bother about, they make no essential difference, such that if this happens, the distance, this is the distance in R2 between alpha of t and alpha of t0. So alpha of t0 I might as well write out explicitly as 0 and y0 is less than 1, where y0 is alpha y of t0. Okay, so this is y0. So this is the point 0, y0. I'll be quite generous and take a ball of radius 1 around it. So in this case it will actually include, that's an invisible color, so let's look at green. It will actually include 1, but it will exclude -1. Maybe 1 is too generous, because if it was exactly 0 it would be a problem. So let's change that 1 to a half. So let's not draw this circle. In this particular case it includes neither endpoints, but it could include one of them but not both. Yeah, so since we have 2 delta issues, so let's half, and this is less than half. Okay, where alpha 0, y0 is this thing. Okay, note distance between alpha of t and 0. Oh, we'll just contradict it directly. So note the endpoints can't both be realized. Okay, so now by definition, since this is a supremum, okay, so first of all, by continuity, at 1, you can say tau 0 is t0, sorry, as I called it, is strictly less than 1. Because at 1 you are 1, 0, and close enough to 1 you are also you are also positive. So you cannot lie inside this set. You can't have the alpha x is going to be positive close enough to 1. Okay, as alpha x of t is greater than 0 for t close to 1. Okay, so that means there is some point, it's strictly before 1, where we leave and we have these things. Okay, now you note, so this means by definition, as t0 is a supremum, so there exists inside this delta neighborhood, let's call it t1, belongs to, in fact I could just say t0 plus delta, which is contained in this neighborhood, such that alpha x of t1 is positive. Okay. So now by intermediate value theorem, hence alpha x of, if I look at the interval t0 t1, this contains the interval 0 and alpha x of t1, whatever that is, of which is positive. But the thing about the topologist sine curve is it oscillates so much that, so what we have got is this tiny interval, okay, a little orange interval, which we know is contained in the image of this small neighborhood. Okay, but we know that by definition of the topologist sine curve, this is a calculation we'll skip, but you look at the sine p over x, okay, it follows that alpha y of t0 t1, this is actually all of minus 1 1. It's contained in minus 1 1 because the whole function alpha y of every point is I'm sorry, yeah, this is alpha y. Alpha y of this image is actually all of minus 1 1, because given any point you can find a sine, you can find its image in sine of x. So I'll say this is this part, it follows this part, I'll say as an exercise. The thing is that sine keeps oscillating, so after every point you will, if you took the usual sine curve, then after every point you will still attain all values between minus 1 and 1. And so this, in this case, because we have taken reciprocal, between 0 and any point you will attain the value, every value between minus 1 and 1. Okay, so it follows that since, and alpha x will attain, alpha y is determined by alpha x because you're lying on the graph. So it follows that alpha y of t0 equals minus 1 1. Okay, but we cannot have, but either that if, for example, if without loss of generality, let's see, what we had is this y point y0 is greater than 0. Okay, alpha y of t equals minus 1 implies that alpha of t is in distance between alpha of t and this point we had 0 y0 is greater than 1. So a contradiction. My distance and alphas are looking too similar. Distance between alpha of t and 0 y0 is greater than 1. So a contradiction. So we have assumed this distance is, we have taken a ball of radius half. It cannot include minus 1. It cannot include, for example, this point. And you will get a point inside this little interval which will end up at minus 1, which is a distance greater than half from the y0. Of course, if y0 was negative, instead you look at the point on top. Any number less than 1 or even equal to 1 with the, because we have a sharp inequality, will do the trick in place of these. Okay, so this is an important, interesting example. It tells you that even though this is connected, you can't physically get from this point to this point. Okay, because the local structure is bad here. So this is, by the way, not locally connected, because if I took this ball here, well, you have to go out of it and come back. So it's because it's not locally connected. It's also not locally path connected. So these are certain examples we have seen of path connectivity. Path connectivity will not play a significant role henceforth in this course. We will move on to other topics, namely separation properties.